Today I will discuss the uniform circular motion. This motion is also a two-dimensional motion, just like the parabolic motion, but they are different. The uniform circular motion is important, and we will see this motion quite often in physics. Let's now begin with an object moving in a circular path. Like this. So the time needed for the object to go around one circle or completing one revolution, it's called the period, or we can simply use capital T. For example, if the object moves in a circular path completing 20 revolution, let's say in 40 seconds, therefore the time for one revolution will be 2 seconds, and this is the period of this motion. So again, the period is the time needed for the object to move around for one circle. So now let's get some practice for the period of a circular motion using clock hands. We have the hour hand here and the minute hand and seconds hand. So first, the hour hand will move in one circle for 12 hours. So this is the period for the hour hand. Let's call it T1. Or if we convert into second, we'll have 43,200 seconds. Secondly, let's take a look on the minute hand. So the minute hand will complete one circle in 60 minutes. Therefore, the period of the minute hand is 60 minutes. Or we can also say that it's 3,600 seconds. And lastly, the second hand will complete one revolution in 60 seconds. Therefore, the period for the second hand will be 60 seconds. So if we compare the period of the hands of the clock, then the period of the second hand will be the shortest. It's 60 seconds. Related to the period, there is also frequency of the circular motion, and it's 1 over the period. Or we can simply say that frequency is the number of the revolutions in every second. The units here of the frequency is hertz, or we can also say cycle per second. Therefore, the frequency of the seconds hand, let's call it Fs, will be 1/60 Hertz, and the frequency of the minute hand will be 1/3600 Hertz, and then the frequency of the hour hand will be 1/43,200 Hertz. The Earth also has a period for its rotation, and the period here of the Earth is 1 day or 24 hours for its rotation. And the planet which has the longest period for its rotation is Venus, and the period here is 243 days. So 1 day in Venus is equal to 243 days in the Earth. It's very long. In the uniform circular motion, we usually define what is called the angular velocity, or omega. So, if the object is completing one circle in one period t, and the angle for one revolution is 360 degrees, therefore the angular velocity omega will be 360 degrees divided by the period. However, in circular motion, we will often to use the radians for angle, and 360 degrees is equal to 2 pi radians. So we can also write that omega is equal to 2 pi radians divided by the period. And we have the units here, radian per second. Or we know that the frequency is 1/period, therefore the angular velocity omega is also equal to 2 pi times the frequency. And the value of pi here is around 3.14 something, or you can just use 3.14. So here we can say that an object moves with uniform circular motion if and only if the angular velocity omega is constant or unchanging. Let's now get back to our Earth example. You know that the period of the rotation of the Earth is 24 hours or 86,400 seconds. Therefore, if you want to find or calculate the angular velocity of the Earth, the rotation of the Earth, then it will be 2 pi divided by the period 86,400 radian per second, and we get 7.27 10 to the minus 5 radian per second. It's very small compared to the hands of the clock. Oh, by the way, there's a nice story about a philosopher named Eratosthenes who was trying to estimate the diameter of the Earth, and he lived around 200 BC. His method is so interesting, and he found that the value of the diameter of the Earth has an error less than 2% from the real value we have now. And the diameter of the Earth is around 12,756.2 kilometers. The object which moves in a circular path also has a linear velocity v, and the velocity v is the tangent to the circle, meaning that the direction is perpendicular, like this, to the radius of the circle. So if the object is at this position, then the linear velocity v will go like this, and this is perpendicular. Also this one perpendicular, and the value of the linear velocity v is the same. So this one, and this one, they are the same. So now let's find the value of the linear velocity v. We can just calculate that the velocity v is the circumference of the circle divided by the period of the motion, and we get v. So here v will be the circumference, that 2 times pi times the radius r divided by the period. Now, since 2 pi over period is the angular velocity omega, then the linear velocity v will be the angular velocity omega times the radius r. So this is very important, and the units here is meter per second. Keep in mind that the value of the linear velocity v in the uniform circular motion, the value is constant. However, the direction of v here is changing. So there is a change in the velocity here, and it's not constant due to the changing direction of this velocity. Therefore, we have an acceleration in the uniform circular motion. We will discuss the acceleration in the uniform circular motion very soon.